According to the hypothetical deductive method, one formulates a hypothesis, deduces relevant consequences from it, and observes whether these consequences are true or false. Depending on this observation, one can either confirm or falsify the hypothesis. In this lecture, I will focus on falsification and treat confirmation in the next. But before I go into detail, let me note an often stressed difference between confirmation and falsification. In step 4, falsification infers from the falsity of even a single consequence to the falsity of the hypothesis. In contrast, in step 5, confirmation does not infer from the truth of even a large set of consequences to the truth of the hypothesis. Rather, it only infers that one might be more confident in the hypothesis if one finds suitably many consequences of this hypothesis to be true. This is often called the asymmetry between falsification and confirmation. It is widely noted amongst practicing scientists. Albert Einstein succinctly described it as, "No amount of experimentation can ever prove me right. A single experiment can prove me wrong." One should read Einstein carefully here. By proof, he meant valid deductive inference. Thus, he did not deny the possibility of confirmation as in step 5. But step 5 is an inductive inference, not a deductive one. Falsification, as presented in 4, in contrast, is a valid deductive inference. This asymmetry between confirmation and falsification also forms the basis of Karl Popper's falsificationism. Popper's method closely follows the structure of the hypothetical deductive method that I described before. You conjecture falsifiable hypotheses. You seek to falsify these hypotheses by checking whether any of their implications conflict with empirical data. Then you reject any hypothesis thus falsified. Note the distinction between a hypothesis being falsifiable and a hypothesis being falsified. Falsifiability is a property of a hypothesis, or more broadly of a theory, namely that it has implications whose truth or falsity can be determined by observations. Some theories have no empirical implications whatsoever. Popper in particular claimed that astrology, 20th century Marxism, and Freudian psychoanalysis were not falsifiable, and argued that falsifiability of a theory demarcates whether this theory is scientific or not. Amongst hypotheses that are falsifiable, some might be more falsifiable than others, because they have more empirically testable implications. Popper thought that more falsifiable hypotheses are better than less falsifiable ones. Falsification, in contrast, is the event of observing that an implication of a hypothesis is not true, plus the inference that this hypothesis is not true. Falsifiable hypotheses thus need not be falsified, but hypotheses can only be falsified if they are falsifiable. Importantly, Popper restricts his testing method to falsifying hypotheses. In his hypothesis testing method, confirmation plays no role at all. He's very explicit that one should never infer the truth of a hypothesis from observations regarding its implications, and not even increase one's confidence in the truth of a hypothesis. All that falsificationism allows is to record that hypotheses, and by extension theories consisting of such hypotheses, have not been rejected so far. Why insist on such a rather austere program? For Popper, it was the hope of avoiding Hume's problem. Recall that Hume's argument seriously damaged any foundationalist justification of inductive inferences. Perhaps, so Popper thought, science could proceed without induction altogether. Indeed, a scientist who strictly follows Popper's falsificationist program can do so. To identify implications of a hypothesis, his method uses modus ponens. If H, then C. The conclusion from the falsity of the implication C to the falsity of the hypothesis H only makes use of modus tollens. If not C, then not H. Both of these are valid deductive inference rules. By arguing that science does and should proceed by deductive inferences only, Popper concluded that the lacking justification for inductive inferences was not so damaging after all. However, Popper's cure against Hume's problem might be worse than the disease that it is aiming to fight. This is because it forces science into a very austere program that scientists, in fact, do not satisfy in their practices, and that they arguably even should not satisfy. In the following, I'll present 3 arguments against Popper's program. The first worry is that Popper's deductive program does not allow scientists to distinguish non-falsified hypotheses according to how confident we are in them. At any given time, there'll be many such non-falsified hypotheses. Some of these will contradict each other. Some will be connected to a lot of observations scientists have made, some less so. Some will have been used in many explanations, some less so. According to Popper, scientists must nevertheless do without judging such hypotheses as more likely to be true than others. That does not describe what scientists really do. They often seem to make such judgments. Nor is it obvious why they should not do this. Popper himself has proposed a measure of corroboration, which distinguishes non-falsified hypotheses according to the number of unsuccessful falsification attempts that they have been exposed to. I think this is an interesting proposal, but it is unclear how this can be part of a purely deductive program. So, as a purely deductive program, Popper's falsificationist account is too restrictive to fit scientific practices. A second worry concerns the applicability of modus tollens for the purposes of rejecting a hypothesis. In scientific practice, hypotheses rarely have immediately observable consequences. Instead, they often require measurement instruments or experimental designs. Take, for example, a simple hypothesis as this liquid contains 3 chemical substances. What are the observable consequences of such a hypothesis? Perhaps one might use distillation, observing that 3 fractions condensate at different temperatures. Or one might use column chromatography, observing that compounds move through the column at different rates, allowing them to be separated into 3 fractions. Yet in order to deduce such observable consequences from the hypotheses, we now need to make additional assumptions about the techniques involved. Even if the hypothesis is true, one can expect to observe 3 fractions condensating only if the distillation operates properly. Similarly, one can expect the compounds to move through the medium at different speeds only if the column is properly prepared. The need for auxiliary hypotheses changes the HD picture considerably. In step 2, deduction of observable consequences is now possible only from the conjunction of the main hypotheses with various auxiliary hypotheses. In step 4, the falsity of such a consequence via modus tollens then only implies that this conjunction is false. And a conjunction is false if any of the conjuncts are false. For example, if we do not observe 3 fractions condensating at different temperatures, all we can conclude is that the conjunction of the main hypothesis and the auxiliary hypotheses are false. And this conjunction might be false either if the main hypothesis is false or if the distillation apparatus does not work properly. Which it is, we cannot tell from the observations we made. More generally, we can say that we never test a single hypothesis alone, but only in conjunction with various auxiliary hypotheses. This is known as the Duhem-Quine thesis after the French physicist Pierre Duhem and the American philosopher Willard von Ornum-Quine. The Durham-Quine thesis considers not only assumptions about measurement instruments, but also such basic assumptions as that there is a world out there and that our sense organs do not systematically mislead us. We might be quite confident in some of these assumptions most of the time, but without them we could not derive any observable implications from a hypothesis. And occasionally, even such basic assumptions are false, as for example, visual illusions teach us. The Durham-Quine thesis implies that in order to falsify a hypothesis, we need to somehow be confident that it is the hypothesis and not the auxiliary hypotheses that are responsible for observing the consequence to be false. But now we're back making judgments of confidence. Modus tollens and deduction clearly do not deliver these judgments. Consequently, the asymmetry between falsification and confirmation breaks down. This, I think, is an important argument against Popper's claim to have found a way around Hume's problem. Falsification, although an important kind of inference for hypothesis testing, faces the same problem of making sense of judgments of confidence and confirmation as other inductive practices do. The previous arguments do not reject falsificationism altogether. They only point out its limitations. Falsification might still be a viable inference method that scientists can use, amongst others. But if they do so in order to falsify theories, they must be aware of the pitfalls of ad hoc modification. Take the historical example of phlogiston theory. This theory, proposed in the 17th century, postulated that a fire-like element called phlogiston is contained within combustible bodies and released during combustion. One observable consequence would be that metals would lose weight when they burned and thus released phlogiston. But it was observed that some metals gained mass when they burned, seemingly falsifying the theory. Defenders of the theory replied that phlogiston might have negative weight, thus saving it from falsification. This is an example of an ad hoc modification, as it does not serve any other purpose but to prevent the falsification of a theory through a particular observation. Of course, not all modifications are ad hoc. Many modifications of theories that were previously falsified often generated important new scientific insights. The criterion that Popper himself proposed is that a modification of a theory is ad hoc if it reduces that theory's falsifiability. It is those kinds of modification that must be avoided. Thus, to conclude, although Popper was right that falsification is an important inference in science, if ad hoc modifications are avoided, he overstated its importance in at least two ways. First, due to the Durham-Quine thesis, scientists cannot avoid making confidence judgments about hypotheses even here, so that the asymmetry claim between falsification and confirmation isn't really true. And second, despite its appeal in avoiding Hume's problem, falsification as a purely deductive program is too austere a framework for the needs of scientific inferences. In the next lecture, I therefore turn to the question of how observations can confirm hypotheses.